Okay, welcome everyone. This is chapter 12, and we are going to talk about spatial data modeling and visualization. So I was a bit like very enthusiastic to learn about how to make maps with R, and I have even participated to various competitions such as the 30 Days Map Challenge, which is very useful to get practice practice with this topic. So within learning how to make maps and things, I've discovered quite few differences that are very important to focalize on and to understand better this topic, which is very, very interesting. And so in this chapter, we are going to have a look at how to model and visualize spatial data, like make a map and things. We learn how to make a map. At the same time, we understand basic concepts of spatial data, such as the differences between spatial data models, and spatial models. So those are three different part of the of this topic that are interacting to each other, and they have a little like tricky difference that might like put you thinking that you are doing something instead you are doing the other one. Then so the chapter is quite long, and so we are going just to have an overview of what's inside the chapter. So if you are interested, I warmly suggest you to read it through and use the code inside it, because you're going to learn a lot. At the same, so we will be using simulated data for general infection, and then put this infection into a location, and at the same time simulate like networks, individuals that interact to each other, and then for this reason might influence the spread of infections, and put this all of this inside a model. So as I said, we won't be able to go through everything today, but you will have the time to read it through if you're interested in this topic. So I like infectious diseases, I maybe sound like strange things, but it's quite fascinating, the things that something that started with by nothing, it like spreading very fast and creating lots of issues. Okay, so for example, Ebola is it's a viral disease. It's like scary thing just to hear the name, that can cause severe illness and deaths. It is transmitted through direct contact with like body fluids, obviously from an infected individual. So this disease is endemic. That means that it is still within certain region of Africa. You can find it. But in particular, just to have a quick visualization, okay, what's happened when something like such as COVID-19 that has gave us like to the world the real meaning of what's happening when a disease spread that fast. So the Ebola outbreak in West Africa between 14 and 16 was the largest in the history. And here there is just like a little chopping things that I've taken from, I don't know if you can.
MSF describe the out.
Can you hear it? Could you hear it?
I've got a little bit, yeah.
No, just to, because it's very short, so I don't know if you can.
All right. Yeah, I heard it.
Can hear it? Okay.
MSF described the outbreak as unprecedented. The worst was yet to come, with the epidemic spreading faster than the response by the international community. The response by spreading faster than the.
Okay, so for example, this like spreading fast. Okay, it's very important to be able to visualize and eventually be able to see the patterns, how this thing is spreading within a certain territory, how where it's going. It's going more on the north, more on the south, because it's the density, because of the density of the population, because of you know, just that someone that moved around the country. What is the velocity of this spread? So obviously, to think about those things and try to put those elements into a model, you need to visualize. And making maps is quite interesting topic. Okay, so what we have just seen is just a map. Okay, so and that is spatial data, such as, you know, latitude, longitude, shapes of the data, if it's a polygon, if it's a line, if it's just a point. But then data can be represented in various formats. Can be a raster, okay, or like some points together, so a vector of data. But we also have data models. So that means that you have some data and you apply modification, some spatial data, such as point, vectors, line, polygons, and rasters, and you are making a modification to this data. You model the data, but you are not making spatial modeling. You are making data models, spatial data models. So you are changing those things. But then you want to make a model for forecasting some changes within this map. So you're making spatial modeling. Okay. So these are 3 key elements to think about. So you are looking at spatial data, adjusting spatial data with models, and then you apply spatial models. Okay, so that is very important to focus on. Seeing that all of us within this book club now have some experience making maps, so I can safely jump this part. And if I go to my book, I think I can just change tab here. And you should be able to see it. Okay, so what is done in this chapter is basically going through starting from the basic, how to make a map without color, adding colors, so identify the polygons and adding colors. Then there is some information about the coordinate reference systems, the boundary box, and the grids that you can create. What are they? So the coordinate reference system is very important, and as its name, it's its coordinate reference system. So identify the points into a specific location. And so we have a nice world. Okay, so as the same, we have different time zones, we have different coordinate reference systems as well, because when you set with the simple feature package, DSF package that we just mentioned it before starting the recording, we talk a bit, we have experience with this package. So it comes with very interesting functions, very useful. And so, for example, just in the just to reference the coordinate reference system, you have this st_CRS, which allows you to extract the coordinate reference systems of a simple feature data, type of data, or set some different coordinate reference system. At level of making a map, what these things can, you know, you can, what I thought when I started learning those things, that why I should define a coordinate reference system. I don't know, I'm not a geographist or something like that. So I'm an actuary, I did statistics, actuarial science, mathematics, and those things. So got into this topic, found it very interesting. But then I said, I make a map, why I should care about coordinate reference systems. Okay, in terms of making a map, coordinate reference systems, it's very important for you to like turn your point of view into the direction of that specific coordinate reference system. So if you are like, it's like you have a world and pointing this, so you are looking like at Europe as your center of map. Imagine the spherical visualization of the world, and then if you change the coordinate reference system, this will allow you to see another point of the world as a center of your map. So if you are, obviously what I thought, okay, but I'm mapping Africa, I'm not mapping another point of the world, why I should care about coordinate reference systems? So I'm just looking at Africa. But then the map can turn a bit like as it's looking to another point. Okay, so it's very important to have a correct coordinate reference system set within your data, because then you have a correct visualization of the location that you are looking at. And so this is just to give you an example, this WGS84 is the most widely used, because we have this Europe, Africa thing on the center as a widely recognized point of view. Okay, so this is the most world geodetic system established in 98, in 84, sorry, in 1984. And what is this? It is just like latitude and longitude that are here and are basically like things like that are built within the grids of your map as a, you know, as I said, to center your point of view on a specific location. In fact, if I, okay, I'm not going into this, but so we have this various function to set a particular coordinate reference system, to change a coordinate reference system. If you, I don't know if you know about this, we also have two types of coordinates. Okay, we have latitude and longitude, as we all know, and then we have the datum. Okay, that means the distance in meters. They are not just in just as we know the latitude and longitude are in degrees. Okay, but then we can have for and that is usually used for small distances, for identify small distances, the datum, which is the distance in meters from the east or from the north side. It depends how you specify. So, and you can switch between these two. As I said, this one, distance in meters, you would use if you are looking at very short distances compared to latitude and longitude that are just in degrees of meridians and parallels. Okay. And so here I've specified a bit of those things, as well as the boundary box. You can use this function to retrieve from a simple feature object the minimum, the maximum, longitude and latitude, and then so use those things to switch within the various things. This is you can do everything. You can change coordinates, you can modify coordinates, you can add meters, you can change the perspective, you can do many things. Okay, so what we did it here is to like simulate some longitude and latitude, the presence or absence of the infection, and the number of cases, and then here is the temperature. Okay, I had to think about a lot if to use a Poisson for simulation or an R norm, because it's all, usually these are counting things. So you do the cases of an infection, so you are use a Poisson, but the temperature can have normal distribution, which is not said sometimes. So it's very difficult. So just take this for with like considering that it's simulated data. And so here we have a like longitude, latitude, the presence, the cases, and the temperature. And we use this to here a bit of like showing what's inside. We do a couple of maps, and we focus on Central Africa Republic. Why? Because it's the center. It's a nice location. It's very difficult, and it's the very center of Africa. Okay, and so here it's very small, but you can see there is a simulation of these points, and you can see it better in down here. So basically exactly the same, and you can have because I had you can see that there are two different colors, and where is the infection and where is not the infection. You cannot see it very well, but that is just to show how to someone who doesn't know how to do that, how to represent these points. Then we start with spatial modelings. For doing this, we look at the correlations of the predictor, just as the same as we were doing a simple modeling things. We use a Pearson method to look at the correlation between cases and temperature. We see that there is no, in this case, within this simulated data, it's a weak linear negative linear relationship between the number of infectious individual and the temperature. And that's okay. So we go forward and we want to have a look at what is happening in here. So we do a little histogram and look at the distribution of the temperature. So as you can see, there are less infectious people than infected, which is good. But here we see the infected individuals within the temperature. We see that when the temperature like is within a certain range, the infections are quite stable. Then if it gets very warm, they go a bit like start decreasing. But these are looking like a bit of outliers. So we can say that are like around very stable within a range that is within 20 and 27 degrees, more or less. So they, anyway, spreading within this temperature, this range of temperature. But what's happened? We ask, okay, this is fine. This is what's happening within our region, but how can I model these points to see what's happened in another part of the region where these points are not available? So I do not have observations for some areas. So I need to create a grid. Okay, to create a grid, that means that I can create a square, which is usually called a window, okay, of fitted points, and then attempt to calculate the distances within my observations and those points. Or I can even cover the entire area with my grid. Okay, this depends by your research question or your analysis. If you are focusing on a particular window, there is lots of resources where you can gain more insights about those things. But for here, I just shown how to create a grid, okay, with this expand grid function. I use the box. This was very fascinating to me, to be able to create these points. So you have this with the box, you point into the max and the minimum and the max of the both latitude and longitude, and then expand the grid. Then you can create a data frame and use this function, point in polygons. And this function is very, very useful because basically from the box grid and your data, identify the points. And so then you can have this grid, this full grid. And here there are both representation, just the window, the window grid, and the entire grid. So how to visualize those things. Then going back to the purpose of these things, so the temperature, what's happened within the temperature. So we can have a look at the temperature, creating a raster. And so there is a Terra package, which is very nice. And within the years, there has been a lot of adjustment modifications. So before was RGDAL, and then has been like retired or something, so put aside, or and everything flow to the Terra package. So now obviously those things are changing continuously. For now, I have saved my REMV log file for this book. So when it will be released, the printed version, I will open up my GitHub repo, and you have the chance for downloading, for like retrieving the version of each package I use within the book. So with the REMV package. So for now, this Terra package is us taking over the RGDAL and other packages, including some of functions. So you can use this one here. This, for example, is not good because it's not aligned as it should. Okay. So you can create a raster and then use the rasterize function, obtain a data frame, and plot it with a geom raster. So we can see that this is a raster. Okay, this is such as a heat map. Okay, where the temperature, the highest temperature here, for example, are in yellow, and the lowest are in purple. And you can see that some areas, this is all simulated. Some areas have a higher temperature while the other areas have not. So what happens if you put your data inside this this temperature, this raster temperature? So you can see that here where the highest temperature here, so these are you can attempt like making speculations about is this infection spreading because of temperature is high or not. And so you can have a look at these things, and you can even calculate the center of mass. And here is being calculated and pointed the center of mass. Okay. So, and the epicenter of infection. So the center of mass, I can calculate this as simple, like sort of average within the range of the longitude and latitude, and obtain a point, which is this one here, this X, red X in here. And that's the center of mass of the observations that I have. This is another representation how to identify those things, and here is repeated in here so you can see it. And so to make a map, I like ggplot, but obviously because I like to make adjustments, do my own, be able to change everything. I can even use Plotly, and then it can like interact it. But there are other options, such as map view, which is within time became very, very, very handy and useful. So you can just do map view and your data, and you have this thing quite fast, nice, that you can use. Or there is this leaflet and all his syntax. There is tmap as well, another package which is very useful to make those things. In here, for example, I've been able to identify like the area with these shadow things, which is quite nice. And you can even make it moving, like growing, expanding on things, if you need it. And this is quite nice. So you can add a neat map in here, and have this visualization. There is a specification that how you can use this to save this map as an image, because it's not that straightforward. And so that's going back. We have seen a grid of points to attempt identify where the other infection could go, could appear. If we want to modeling this for attempt to find a model to predict the future infections on a different time. We have seen the temperature, so we did a raster and have a look at how the temperature. We visualize the temperature as a base map on the infections, but now we want to see more about these points, because they are not just fixed points. For example, when you are making maps looking at, you know, something that is not moving, you are looking like trees or, you know, distribution of things that are, say that within infectious diseases is different, because and people, because you have these points that moving. So the dynamics, it's a key part. It's very important. And how to have a look at these dynamics. So there is a very nice this package, small world network, that allows you to use this sample small world function. You can this is all inside the iGraph package. You can just, you know, install iGraph, and then you have this sample small world function. Here I shown just how to simulate one, and with setting the number of nodes that are the point of interaction within two people. That's a node. And then each node is connected to k nearest neighbors. So like, you know, that someone can infect someone else, but then if you have other two people around, they can get infected as well. So we consider that these nodes have 3 neighbors. Okay, and then the probability 10%. Okay, that can happen. So we can create a small world. This small world it is just a network, and it's nicely called small world, because it does create a world, as you can see. Okay, and these are all the connections within some data. Then I want to see what's happened if when things change it. So I can use so like define the nodes as the susceptibles, I for the infectious, and I can create a second word, small word, and then make an adjustment. So the status as susceptibles, and the infected as a I. Okay, you can use this V function. I'm not going to have a look at that, but as you can see, it's I put this in the chat, and so it does basically allows you to set the random nodes to a certain status, and then as well you can assign a color when this status is infected, in this case, or not. And then here I plot both of them. And so as you can see here, there are these black points, and those are the infected. Okay, so we have created a network of individuals that get in touch into each other and can infect. So if one is infected, can infect the others. So these are the infected. We don't know how it's going to spread. So going back to our data, we have this Central Africa grid full. So we are looking at the full grid. This one here, where we have these points. Some are infected, some are not infected. What we do is, these are some procedure to use to make sure that the polygons within the coordinates are valid. So they are touching each other and they are covering the entire area. Some time is needed to use this function to make sure that the polygons are valid. It runs are like a sort of double check. And so you can have a look at the documentation. And so what I do here, extract the coordinates of my data and use this to make my small world within my data. And here you can see it. Okay, so the triangle here, red, are the infected, and below you can see there is a network of people, and then so this is people that can get that are around the infected ones, and the lines are the direction of interaction within the points. Okay, so nice to be able to represent this. And then we think about the distances between an infected people and another one, which is here. We can usually is the Euclidean distance, the one that is used, but there are different type of distances that you can use. Very basic. What is the Euclidean distance? How to make a function to calculate Euclidean distance. And then we are going to use it, but not for now, because we are considering spatial autocorrelation. So what is spatial autocorrelation? Two points are close to each other, so they have an highest, what is this balloons things? I haven't touched anything. So this spatial autocorrelation is basically an highest probability of something happen when 2 points are close to each other. So obviously that if I use 2 points that are close to each other and something happened within this this area, those points are correlated to each other. That things that happen within these 2 points is more likely to happen there than in another place. So this is autocorrelation, and it is very important to be considered. So here is like it's there is a law which is called Moran's first law. You can use adjustment variants of this law, like a global Moran's law. This chapter requires a bit of like passion for spatial data if you are interested in it. So we can use this SPDEP package, and which provide this various function that we can use, included the Moran test function. So we can run and have a look, set the coordinates, use the coordinate function, and set them to longitude plus latitude, define the neighbors with the neighbor function, apply to the coordinates, and then create spatial weights. These weights, what are they? That points that are close to each other have a higher weights than points that are farther to each other. Okay, so it does basically create a neighbor list of weights that then you can use and say, these 2 points are closer. Where is it? For example, these 2 points are closer than these other 2 points. So this couple will have a higher weight than this other couple. And so you can use that to make a consideration about the highest probability of getting infected for that one that has a highest level of weight than another one. And so we have this list of weights, and we use this Moran test to run a statistic and see that the result, it's negative.
I think just frozen.
Yeah, I think so too. We could give it a couple of minutes, see if she comes back.
Okay.
Otherwise, I presume if we can just hit stop on the recording.
Yeah, maybe let's